Hi everyone, my name is Margot Leibold, and today with Harshit Saokar, we're going to be presenting on ServiceRouter, Meta's Hyperscale service mesh. But before we get into the details of ServiceRouter, I want to describe what we mean by hyperscale. Like many large companies, Facebook runs as a distributed microservice architecture. Let's take the example of a Facebook user loading their newsfeed. That user request will first hit our front-end web service, which is responsible for aggregating all of the information that we need to be able to serve that newsfeed. It will do this by fanning out these requests to potentially multiple back-end microservices. You can think of these like photos, newsfeed, reels, profile, etc. And those microservices may further fan out to other downstream systems like databases or storage. This chain of requests can get quite deep. A single user request may trigger up to 10 subsequent backend microservice hops. And as we add more hops, we add increased complexity in the routing. So what do I mean by hyperscale? Let's talk about numbers here. Facebook runs tens of thousands of microservices that are all talking to one another. And we're sending tens of billions of requests every second through these microservices. Furthermore, these microservices are running on millions of backend hosts. So we're talking about scale that requires a lot of efficiency and optimization in routing. But let's see how scaling a single application can add complexity to RPC routing. First, we'll start with the example of a single client talking to a single instance of a service. As this service scales, it will typically do so by replicating across multiple instances. This is great, but now the client has a problem. How does it decide which of these instances to actually send a given request to? We need to introduce a robust selection algorithm that the client can use to determine which host to send that request. Let's scale even further. Meta runs 21 geo-distributed regions, all across America and even parts of Europe. In much the same way that a plane flight time takes longer with the distance between destinations, so too does a request take longer to travel between different regions. So you can think of a request that originates on the West Coast would be much better served by a data center that's also located on the West Coast than having to travel all the way to the East Coast or potentially even to Europe to be able to serve that request. So this introduces the second complexity. How do we first choose a region and then second a host within that region that actually has the available resources necessary to serve that request? Okay, so we're taking latency into account, but what else? As I mentioned before, Facebook runs across millions of backend hosts, and at any point in time, some of these hosts may be down or unavailable. This is expected. There's common reasons why this may happen. For example, a host may be disconnected from the network. It may be undergoing standard maintenance. It may be overloaded. And the client needs to make a smart decision to route around all of these types of failures to ensure that it's finding a host that is healthy enough to be able to serve that request. So given all of that, I'm first going to pass it off to Harshit, who's going to give us an introduction to Service Mesh and the novel properties of ServiceRouter. Then later in the talk, we're going to get into some of the unique features that ServiceRouter offers to be able to efficiently do routing at scale.
Thank you, Margot. Hi, everyone. I'm Harshit Saokar. I've been working at Meta for the last 5 years, primarily focused on our routing-related infrastructure. I want to start with what Service Mesh is and how it helps with sending requests efficiently between services. The textbook definition of Service Mesh is that it is a dedicated infrastructure layer that provides a way to manage communication between microservices. This allows service developers to focus on actual business logic as opposed to building a boilerplate related to communication. Service Mesh provides key features such as logging, fault tolerance, security, load balancing, and service discovery. Service Mesh consists of two logical entities, data plane and a control plane. Data plane's job is to shuttle the actual data over the wire. Often, this is implemented as a separate process called sidecar. Client binary proxies the request to sidecar running on the host, which then does the job of actual routing to the remote host. Control plane is responsible for deciding the routing policies such as various timeouts. Control plane changes can be authored by developers or by automations. Sidecar subscribes to the control plane updates and applies them in a real time. So why do we need this separation between data plane and control plane, you must be wondering. So one huge advantage of this approach is that it allows easy reconfiguration of the system. We do not have to wait to deploy a new sidecar binary if we only have to change a small timeout. This whole system of sidecar proxies shuttling the data and control plane managing the routing policy is collectively a service mesh. I mentioned that service mesh is typically bundled as a sidecar process. However, this approach incurs an extra hardware cost because requests are going through an additional hop. At our scale, that cost was huge. So we avoided using sidecar wherever possible. Instead, we used a library approach. Our service mesh library is directly linked into the client process. One limitation of the library, though, is that one has to implement service mesh in every programming language being used. So for rarely used programming languages, the sidecar is much easier to maintain. So we run both the flavors at Meta. 1% of the requests are routed by sidecar and dedicated proxies, but 99% of the RPC requests are routed by our library. If we were to completely switch everything to use sidecar, we would waste capacity equivalent of tens of thousands of additional machines. This simple design decision provides us with a great deal of efficiency. So what is ServiceRouter? ServiceRouter is Meta's service mesh. ServiceRouter has been in production for 10 years. In all of Meta's microservices, use this service mesh for the communication. We support heterogeneous set of services such as microservices services and services with streamed RPCs. ServiceRouter leverages the idea of control plane and data plane separation well. The data plane consists of ServiceRouter library running in a client process. We use Apache Thrift as our RPC protocol. On server side, the Thrift server module is responsible for deserializing the response and invoking the application code. Client discovers the servers through service discovery system. It subscribes to service discovery system to resolve the name of service to its endpoints. Once the initial subscription is made, updates are streamed directly to the client. Server updates service discovery system when its IP or port changes. Our service discovery system is powered by geo-distributed deployment of Zookeeper, so it is highly available. Control plane of ServiceRouter consists of critical modules that help it manage its routing policies. First, Config Manager is what our developers interact with to store common routing settings such as various timeouts or load balancing strategies. ServiceRouter reacts in a real time to the changes to this configuration. This property becomes immensely useful when mitigating production issues via routing related fixes. Next, cross-region routing module is very distinct in its design. The main task of this module is to periodically push the updates to ServiceRouter to help it choose a region that satisfies both latency and load requirements of the service. We'll talk more about this later on. The last module provides information about how to log traffic telemetry. ServiceRouter logs rich telemetry, including details such as why it selected a certain host and whether request finished successfully. This may appear a trivial feature, but I want to emphasize that this rich logging made ServiceRouter a default routing library at Meta. Our developers loved ServiceRouter's ability to easily troubleshoot routing related issues. This propelled our widespread adoption. So now we know how to build service mesh at a high level, but how would we measure its success, especially at a hyperscale? One table stake metric is error rate. We want service mesh to reduce errors, especially the errors that are happening due to misrouted requests. But beyond that, what else is important? Over the past years, we have observed that there are two advanced metrics that our developers want service mesh to optimize for. First, they want good load balancing. The load imbalance in the service can significantly increase its operating cost. Second, they want requests to finish faster, that is with low latency. This is even more important to us because our products power real-time communication between people. I mean, we all want our WhatsApp messages to deliver instantly, right? Now, I'll invite Margot back to talk about our first success metric, efficient load balancing.
Thanks, Harshit. Now we're going to talk about how we can efficiently do load balancing at scale. In this example, we're going to have two clients talking to a service that's replicated across 5 backend instances. And the naive approach here would be for every client to talk to every backend instance and balance load across the entire service. But as you can see from the number of arrows already in this diagram, this quickly becomes unscalable. As the number of clients and the number of servers grows, so too does the number of connections that are overall maintained in the system. And maintaining excess connections can be expensive for both client and server. So to combat this, most service meshes use a technique called subsetting, where each client will talk to a fixed subset of the overall hosts in a service. In our example, each client is talking to 3 of the backend hosts. ServiceRouter sets a default selection size for most services. However, we also allow service owners to customize this property based on their unique service profile. So given that, now we're looking at a single client with a subset of 3 hosts, but we still have to choose one of those 3 to actually serve any given request. And this is where typical load balancing techniques come into play. Once again here, the brute force option is that the client talks to each of the hosts in its selection and compares the load across all of them to choose the least loaded. But this is also becomes expensive because we're talking to every backend server. In fact, there was a famous research study in 1996 called The Power of Two Random Choices, which postulated what would happen if we instead chose 2 hosts at random first and only compared the load amongst those 2 hosts. It's unintuitive, but surprisingly, this algorithm actually shows no degradation in the overall load balancing, but is much more efficient for services at scale. So ServiceRouter deploys this pick 2 technique to actually choose 2 hosts at random and only compare the load between those 2 hosts. But we still have to get the load. And the way that we can do this is through a technique called load polling. A client will first send 2 blocking requests to the backend servers to fetch the load, and then it will compare the load between those 2 and choose the lesser loaded. This works well because the load information is very fresh. We've just requested it from those backend servers, and we can make an informed decision about the load balancing. However, we're introducing some inefficiencies here as well, because we just introduced 2 blocking requests in the critical path of the RPC just to fetch the load information. This can affect the overall latency profile of a service and make a service less efficient. To see why this is a problem, let's take a look at this histogram which shows the average latency of various microservices at the company. As we can see from this diagram, many services at Meta are actually running at low latency, with average latencies of under 15 milliseconds. For these services, doing load polling can be prohibitively expensive, as the extra overhead that it requires can make it not worthwhile to actually serve those requests. So to combat those inefficiencies, ServiceRouter offers a second load balancing technique that we call load piggybacking. In load piggybacking, a server will piggyback the load with every response that it sends on a typical RPC. And it does this by fetching the load information, attaching it in the metadata of the RPC response, and then the client is able to access that information essentially for free and cache that information to use for future load balancing decisions. So this load gets cached locally on the client, which means that it's very minimal overhead. We're not introducing any extra RPC hops or added latency to actually acquire that load information for future requests. And this works well as long as the cache can stay relatively fresh, which means that we need to be receiving responses from the server pretty often. However, there is the potential for this cache to become stale if we're not receiving responses from a given host frequently enough. So there are pros and cons to both load balancing algorithms. And historically, ServiceRouter required that service owners manually choose between one or the other based on their unique service profile, comparing the QPS and latency profile of their service. But we later realized that the ServiceRouter library actually has all of the information it needs to be able to construct these heuristics and make a smart load balancing decision on behalf of that service automatically. So with that, we introduced a new algorithm called automatic load balancing, where the client will cache and remember recent history about a service's QPS and latency profile, and it will use this information to dynamically change the load balancing algorithm on every request based on what the load values currently are. So we can see in the flowchart below how this algorithm works. We first ask ourselves, is the load cache fresh? If it's fresh, that's awesome. We can already use that load. We've already have it cached, and we can make an informed load balancing decision with no extra overhead. This is the best case scenario. But if the load isn't fresh, or if for some reason it's otherwise unavailable, then we have other things that we have to consider. We need to think about the latency profile of that service. Services that have high latency sensitivity, meaning they're very low latency service, and introducing extra latency to that service can be prohibitively expensive, those services can't use load pulling because the overhead of load pulling adds enough latency to make those requests unavailable. So for those services, the best option is actually to just use random. But for services that aren't latency sensitive, that may have longer latencies or don't care about their latencies as much, load pulling can be a good option, as it gives us that fresh load information and allows us to make an informed decision. We can see what the impact of automatic load balancing is on one of the major services running at Meta in this chart below. The y-axis here is the spread of load between different hosts in a service. So a larger spread here indicates that there's more load imbalance. Some hosts are underloaded while other hosts are overloaded. In an ideal scenario, there would be no spikes whatsoever, and every host in a CPU-bound service would be running all of its CPU. We can see that the impact of enabling automatic load balancing here significantly converges on those spikes, and we see that the load is better balanced across all of the hosts in that service, indicating that we're better using our resources. Automatic load balancing works great for a few services, and eventually we enabled it for every service at Meta by default. However, load balancing isn't the only thing that we must consider when trying to decide where to route a request. So with that, I'll pass it back to Harshit, who's going to talk about how we do low latency routing at scale.
Let us look into how ServiceRouter reduces the overall request latency. Our main source of latency is geo-distributed nature of our data center regions. Choosing a right region usually shaves off hundreds of milliseconds of network latency. To balance the load across regions with comparable latencies, ServiceRouter assigns regions to the latency-based concentric rings. These rings are derived from historical latency data between the regions. Client does a local decision to pick the servers in the innermost ring. This works for most services. However, some services want more control over how much traffic each region should receive. For these, we delegate the job of finding optimal region to the control plane. Cross-region load balancer is a control plane module that is responsible for providing this hint to the clients. Its job is to generate source-specific routing table which tells how often clients should pick a certain region. This module observes traffic demand and capacity supply at a regional level. If the service is running hotter in one region, the module shifts traffic to the nearby regions. It is important to note that this design introduces the centralization without having to forward the request through dedicated load balancers, because those typically incur a higher cost. Establishing a new connection is another contributor to the latency. Setting up a connection involves extra round trip needed for TCP handshake. This overhead could be huge when requests are going cross-region. We utilize a common technique of connection pooling, wherein each new connection is cached and reused by the client for subsequent requests. There are other advanced techniques that we use to avoid connection-related latencies. I encourage you to read our blog at Scale site to learn more about those. To summarize, over the last 10 years, ServiceRouter has evolved into highly scalable and reliable service mesh that all of Meta's services depend on. If you are beginning this journey of building scalable service mesh, we have few takeaways that can help you. First, if you own the source code of your clients, you can reduce the cost of service mesh by embedding it as a library. This is more cost effective than sidecar. Second, service mesh can adapt its load balancing policy based on latency profile of the services. This helps services maintain desirable load balance while keeping the overhead of latency low. Third, control plane can help in low latency routing across regions. This approach scales better than centralized load balancers. This concludes our talk. We are very happy to share that ServiceRouter paper has been accepted in OSDI 23. We encourage you to read this paper to know more about us. Thank you for listening to this talk. Hope you have a great day.